Yeah, and we're live. Excellent on a Tuesday, gloomy morning outside. Oh my. All right. I see there's 16 people so far. Where are the rest of them? Oh, 17. Where are the rest of them? They're all going to be sad that they missed me on this wonderful morning. Here I am teaching to an empty classroom, which is strange, but not unexpected at one point or another in my career. But I don't know. It is what it is. Whoa, it just jumped to 25. That's a lot of people in this chat. Now it's down to 20. Okay, I'm going to stop talking about that. Anyway. Yeah, so here we are. You're at home. I'm in here. We're teaching. I have you Tuesday, Thursday this week. Oh no, my microphone. Everything's just going off in haywire. It just seems like this whole week people are just so extra tired or something along those lines. Probably because of the 4-day weekend. We need like a recovery from that or something along those lines. I don't know. Whatever it is, it is. Anywho. So for you guys that are here, which some now is now 13 people, strange. For you people that are here, I had assigned for you guys just to read chapters 6 and 7 in the textbook. Last week, we ran into a little bit of a technical issue. I believe I had posted about it, but I posted about what was the actual issue. For some reason, my desktop computer connected to the hardwire connected to the internet kept working, but the wireless connection from my phone, being the webcam, sending the signal to the computer, that was disrupted, which is very strange. I don't know, made me sad. I don't know. It's such a weird week last week, but it is what it is. The Wednesday that we had. Yeah. So, I know I'm going off on a weird tangent. In terms of today, I plan on continuing my lesson on linear regression. We're going to hit some of the things that I was hoping to hit last week, but we'll see what happens. Before I leave here today, I am going to be assigning you some problems from the textbook. I won't assign them during this lesson. I'm going to assign them before I leave the building today because I have more time to do that after the fact, not just throw that on Google Classroom, which would be great. Anyway, but yeah. Now, the unfortunate thing about teaching from the classroom is that all of you are going to have to deal with that little glare right there, which is like just very frustrating to say the least. I have requested OBS Studio for my computer so that I can stream in a much more efficient fashion. So far, I have been denied, but I will not give up. I also requested that I teach from home, but of course, we all saw how that went last week. But anyway, if you would, ladies and gentlemen, I'm going to need those notebooks out and open. I'm going to meander over here to my table so that I can teach appropriately from dislocation. And we're actually going to start. I'm going to have your notebooks out, of course, but what we're going to start with is actually a problem from the textbook. Let me see if I can get this correct. All right, let me try to reload page 195, page 196. Good. And I want to zoom in right down there. I want to zoom in on the bottom down there. I think this will work. I really hope this will work. This might work. Good. Okay, good. But you don't have to have the online textbook open if one does not want. The only thing that you really have to worry about is this particular problem. Now, I tried to get it out of the glare as much as possible. I don't really care so much for the numbers at the bottom. I'm going to talk about what those numbers mean at the bottom when we actually get to something like that. But the first thing that I want to do is I want us to enter this data into our graphing calculators. Now, if you're having a little trouble reading the numbers, of course, I will read them off when I enter them into my calculator. But I would like you to enter this data into your graphing calculator. Capacity in terabytes, I would like you to put into the L1 for your X list, And price in dollars, I would like you to put into L2 for your Y list. And like I said, I will read those off if you can't see them, because obviously you're looking at a screen but I'm going to enter them in myself as well. Boom. Now, being that you are opening up your graphing calculators on your computer, of course, everything is reset. We'll take care of the diagnostics in a little bit, but let me enter in the status. So I'm going to hit stat, and this is what you would do as well. I'm going to hit stat. I'm going to hit enter on the word edit, and I get to L1, L2. You can kind of, hopefully you can see that right there. There you go. Look at that. L1, L2. In L1, I'm going to enter in the following numbers. I'm going to enter in 0.5. That's a 0.5, of course. 1, 2, 3, 4, 6, 8, 12, 32. I'll repeat those just one more time, and then I'll get to the Y list. In L1, you are going to enter in 0.5, 1, 2, 3, 4, 6, 8, 12, 32. If you do have your textbook open, it's page 196, but again, it's just easier this way. Now, this is going to be a little bit, I'm going to read these a little slower, the Y list, so we can kind of do this all together. In the Y list, in L2, you're going to enter in 59.99, 79.99, 111.97, 109.99, 149.99, 423.34, 596.11, 1079.99, and 4461. I'm going to type these numbers in here just so we have them in the, I can actually type them into the chat as well. So X list, the following numbers, it would be 0.5, 1, 2, 3, 4, 6, 8, 12, 32. There it is. Yeah. The Y list, be 59.99, 79.99, 111.97. Again, double check your numbers because I want to make sure that we all get the same results, because you are going to be running the linear regression on your own. 423.34, 596.11, 11, 1079.99, and 4461. That should be your Y list right there. Just double checking my numbers, making sure they're all correct. Good. Okay. So we are going to run a linear regression, but of course you need to have your diagnostics on, just for the sake of argument. Having the diagnostics on are going to do that calculation for the R value, for the correlation coefficient. Now, at the end of the lesson, before it screwed up on me last week, we were talking about the different characteristics of the correlation coefficient. Measures the strength of the correlation. Whether it's positive or negative determines the slope of the line, whether it be positive or negative, of course. You can only measure R between -1 and +1, -1 and +1 being the strongest and 0 being the weakest in terms of a linear association. Whenever you hear the word correlation, you need to think of it as a linear association. We'll deal with that when the time comes. So I'm going to switch my camera over. so you can see what I see on my calculator. But we are going to have to turn our diagnostics on. Move that over here. Let me see what it's like on the screen. Now it's better over here. It was definitely better over here, avoiding that glare. Anyway, we're going to have to turn the diagnostics on, and the best, fastest way to get there, if you hit second zero, it'll take you to the catalog, which is an alphabetical listing of all the functions that are on your graphing calculator. Fantastic. Now, you could scroll down to the Ds. Or you could find the button that has the little green D on it, which is this one right here. Now, it's already alpha locked. But if you hit that button, it'll take you directly down to the Ds, so you don't have to keep scrolling. But if you hit that button, boom, it takes you down to the Ds, and I got to turn my diagnostics on. You got to turn your diagnostics on. Otherwise, the calculator will not calculate R and that elusive R squared, which you don't necessarily know what that R squared is just yet. But we'll deal with it. Chapow. Chapoo. There it is. That's all it really took. Diagnostics on. Now I need to run my linear regression. So I'm going to run my linear regression. I'm going to hit stat. I'm going to go over to calc. I'm going to go down to linreg. Now, again, my function for linreg is different from your function for linreg. On your function for linreg, it does ask you for X list, Y list, and that all fun thing. I don't know, weird blah, blah, blah. You don't have to change it as long as you entered your X's into L1 and you entered your Y's into L2. As long as you've done that, then you should be fine. Just as a side note, as long as you've done that, you should be fine. So let me hit enter here. Ba-boom. And it calculates all of those wonderful numbers for me. It calculates my slope. It calculates my y-intercept. It calculates an r squared, which you don't know what an r squared is yet unless you read the chapters. And it calculates an r. Now, as we said, R is the correlation coefficient. It measures the strength of the linear association. Now, this R value is very close to +1, which means if you have an R value of 0.987, then you have something that is pretty strong. You could, like very strong, you could say. It's not the strongest that it could be, but it is pretty close to being incredibly strong. Well, let's take a look real quick. Let's just take a look at the scatter plot. Now, again, this is one of those things, graphical displays on the graphing calculator. You should be able to see what the scatter plot looks like. Because looking at the scatter plot, one of those assumptions and conditions that you eventually have to hit is the fact that the scatter plot has to be quote unquote straight enough. And there's something else that we're going to do with that in a little bit. You go, ooh, you're gonna hate it or love it at the same time. I don't know. But let's take a look at the scatter plot. If you hit second y equals, it'll take you to your stat plot where everything, of course, is turned off. You turn the first one on, enter, turn that thing on. The type is automatically set to scatter plot, and your X list and your Y list should automatically be set to L1 and L2. Of course, if you hit graph right now, nothing will happen. Because if you hit graph right now, you won't see anything. Everything is way off the screen according to the numbers that we typed in. So I'm going to have to zoom 9 it. If you hit zoom and 9, zoom, and the 9th option is zoom stat, you will actually see the scatter plot. Now, something interesting is kind of happening with the scatter plot. Something very interesting is happening with the scatter plot. Obviously, these numbers, the last number in particular, appears, and I'm being very precise with my language, appears to be an outlier. I don't really know what the heck's going on here. I mean, I guess it looks straight enough. Just looking at it, it looks straight enough. One could make one can make an argument that this thing might be exponential in nature. But if you're just strictly talking about correlation, you are strictly thinking about the linear association. And I guess it could be linearly associated, So, I guess it looks straight enough. So again, those conditions that we talked about, I'm just going, flip back to the screen. Going back to these numbers. These are the numbers that we dealt with. The data on disk drives we saw in chapter blah, 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 blah. We want to protect price from capacity. Price from capacity. That whole thing. Oh, nice. Oh, I can double check these numbers to make sure that we did it right, of course. I'm going to talk about printout output data in a little bit, or later today, I should say. But the variable and the coefficient, usually you'll see these on an output for linear regression, and these are pretty much your slope and your y-intercept. The coefficient of the constant being the number by itself, that is your y-intercept. The coefficient of the variable for capacity, which is the coefficient on the x variable, mx, that would be your slope, 142.177. And I can double check those numbers against what I got here. Flip the screen. Yep, I got them exactly. So I'm just confirming that I typed them in correctly. So we're good there. Excellent, excellent. And in fact, they do give you this weird R squared thing, which again, I have not written down a definition for you just yet, but they give it to you as 97.5%, which if I flip back to my screen over here, you can see R squared is 0.975, 97.5%. Okay, fantastic. Now, these are not the questions involved with this problem. I actually don't care what the questions are for this problem. I don't. I'm using this problem as a means to an end. Number one, reviewing the different steps that you could take to run that linear regression with your diagnostics on, but also to talk a little bit more about the details that are involved with this problem. Ooh, yeah. It's going to be amazing. Now, one thing I'm going to point out. If you turned your diagnostics on, yes, you did get R and R squared. Great. But there's something else that you got as well. There's something else that you got in your calculator. If you hit second stat, you're going to come to an interesting screen here. Second stat brings you to this list of lists. It brings you to the name or the names of all the lists that are currently inputted into your calculator, which of course you have L1 through L6. Those are default. But because you ran a linear regression with your diagnostics on, you got this extra list called resid. Now again, if you read ahead, you would know what that resid is and what it represents. That resid represents your residuals. Now, what the heck is a residual? Hold on. Let me do something real quick. Let me take this and store it into my Y1. You can just look at my calculator right now. You can just see that I just made the calculator store the equation into my Y equals key, which is nice. I'll teach you how to do that another time. And you can see there is the line of best fit. Now, again, I'm going to write down this definition for you when we actually write down some notes, because you already have your notebooks out and open. But a residual is the vertical distance away from the line of best fit a data point is. So, for example, this data point right here is below the line of best fit. which means that for that particular data point, it would produce a negative residual. This one up here, clearly it is above the line of best fit. It would produce a positive residual. I'm going to give you the definitions of that in a little bit, written down. Now, what does that mean? How does that help us? I'm going to show you when we get there, because that residual or that residual list is going to help us make a more accurate determination as to the validity of this graph in a little bit. Oh, that's going to be great. Because you could do everything right. Quantitative data, scatter plot looks straight enough. Yes, it has an outlier, so perhaps we're going to run and we are, by the way, we are going to run this analysis both with and without that suspected outlier. We will. We're going to see the changes that are made as a result. All of those are good practice. But knowing what the residuals are is going to be the make or break factor in determining, perhaps it wasn't acceptable for us to run a linear regression. I don't know. Maybe it will be. We'll see. We shall see. So I'm going to go back to my notes, and I'm going to catch you up on some stuff. Zoom this thing back out. Bring over my papers. There we go. Zoom it out, zoom it out, zoom it out. There we go. And let's get down some of this information, first of all. I may be backtracking on some things, but that's okay. Today is December 1st. We made it, crew. It's the last month of the year. Woo! I don't know, whatever. I think so. September, October, November. You're done with 30% of your school year? 30% of your school year. What a life. I don't know, whatever. And we'll call this Lin-Reg continued. Lin-Reg continued. Now, just for the sake of argument, I can see the the live chat. I can see the live chat from where I'm sitting because I have that thing open on my phone. Oh, happy day again. But we'll deal with that. So, a couple of key phrases here. First of all, your X variable versus your Y variable. Now, for the example that we were doing, our X variable was capacity in terabytes, and our Y variable was price, obviously, in dollars. That's besides the point. But there are certain phrases and terminology that you need to associate with the X variable and with the Y variable. Again, it doesn't have to be X and Y. It could be like Q and R. It could be A and B. It doesn't matter. But typically it's X and Y. X is what they refer to as your independent variable. They refer to it as your independent variable, which means for your Y variable, they refer to it as your dependent variable. Or the idea that, well, whatever your X variable is, it is the independent variable in the sense that it can change. It doesn't really rely on anything else. Those were the terabytes. But for the dependent variable, it depends on what the terabytes were. In fact, the price, you could argue, the price would go up dependent upon the amount of terabytes that were in the disk drive. Just as an example. You can also refer to the X variable, and you will see this in certain problems. You will see it referred to as the explanatory variable. The explanatory variable. It explains what's going on with the price. Well, what happened to the price? Well, why did the price go up? Well, look at the terabytes. The explanatory variable. And the Y variable, in turn, its counterpart, something that you should feel familiar with, your Y variable, is the response variable. It's coming back around. The Y variable is referred to as the response variable. Yay. Fun fact. The x variable, again, just terminology that I want you to be familiar with. The x variable is also known as the predictor. And the y variable, and you will see this in various free response problems, is referred to as the variable of interest. It is the variable of interest. That's typically what they're referring to. I mean, we'd be really interested in, well, what would the price be, kind of thing. Or we'd like to do an exploratory on the price dependent on what the terabytes are. Or, and again, I'm going to flip back to this problem, the same problem that we did before. Look at the way that they worded it. Suppose we want to predict price from capacity. The x variable is the predictor. The y variable, I guess you could be like the predictee. I don't know. You're trying to predict what the cost would be from the capacity of terabytes. If I'm the predictor, then I'm the one starting the process, and then the end result is the prediction, I guess you could say. Oh, the word choices with this thing. But I just want you to be familiar with that because, again, they may refer to it as any which thing, you know. So we ran a linear regression. We ran a linear regression based on the x variable and the y variable, and we found an equation which is known as the line of best fit. And sometimes they will refer to it as that. They say, well, find the line of best fit. Now, they may not. Again, the word choices on these things go all over the place. They may also refer to this as a linear model. What is the model? Model the data, something along those lines. And if you hear verbiage like that, they're referring to the line of best fit. They want the equation. If they say, what is the linear model? They're referring to the equation, the y equals mx plus b equation. They will also use the following letters: L, S, R, L. They will also use the following letters: L, S, R, L. Now, what that stands for, and again, if you read ahead, good for you. Least squares regression line. Least squares regression line. That's what that thing is referring to. That down a little bit. There we go. Trying to avoid the big blur of a ball of light in the middle of the screen. If you ever see those letters, they're like, hey, they ran an LSRL on that thing. They're referring to the least squares regression line. They're referring to the line of best fit. I just want us to, again, all be on the same page with that, because you don't know what type of verbiage they're going to use. They're going to use all sorts of different verbiage, and I need you to be ready for it. They all mean the same thing, those three statements. It's just, you know. Now, in terms of your y equals mx plus b, I do have a bone to pick with various problems that you may see in the textbook or multiple choice. But when you are actually finding that prediction line, when you are actually running the linear model, you would not write the equation out as y equals mx plus b. You would not. You would actually write it out, not with a y, but with a y hat. And yes, I am not even kidding you. That is how we refer to this thing. We refer to it as y hat. I know mathematicians are very creative with the ways that they come up with things. It's like, are you kidding me? Y hat? What a ridiculous name. Yes, it is a ridiculous name. Y hat is the prediction model. End quote. If the x variable is the predictor, then I guess you could refer to the y variable as the prediction. But it's not exactly the y variable, it's y hat. Instead of y equals mx plus b, we refer to it as y hat equals b sub 1x plus b sub 0. That's what we refer to it as. Y equals mx plus b with your slope being b sub 1 and your y-intercept being b sub 0. They all mean something within the context of the problem, which we're going to talk about when we get to various problems. You're going to see that in some of the practice problems that you're going to get to. But we'll get there. B sub 1 is, of course, your slope. And it is calculated in the following fashion. Now, here's the wonderful thing about these calculations, these formulas that I'm about to give you. These formulas show up on the formula sheet for the AP test. They do. These formulas show up on the formula sheet for the AP test. Translation, it's not so much that you have to memorize them, but you have to know how to use them. Slope is calculated in the following fashion. It is R, which is the correlation coefficient, times S sub y, S sub x. Those are your standard deviations. Now, I believe last time we were here, I was able to write down the formula for R. That's besides the point. I'm not going to rehash the formula for R. Another thing that I believe they do give you on that formula sheet. But if you take the correlation coefficient, whatever that R value actually is, and you multiply it by the ratio of the standard deviations of the y values to the x values, that gives you the slope of your line of best fit. That is exactly how they calculate it. This is what your calculator does when you run that linear regression. When you run that linear regression, it automatically calculates R based on the formula that we did last week using the z-scores and adding them all or multiplying the two. Then they calculate the standard deviation of your x list, the standard deviation of your y list, put them into a fraction, multiply it by R, boom, that's the slope of your line of best fit. They don't guess. They actually get the exact value, which is nice. It's nice that they're being accurate with that kind of thing. And that's what I'm going to go with. Now, your B sub 0, which of course is your y-intercept, is equal to the following. Y bar, and I'll talk about what that is in a minute, minus B sub 1 x bar. Separate those. There we go. See them a little bit better. Now, what that means is this. X bar and Y bar are your average. X bar is the average of the X values. Y bar is the average of the Y values. You throw them into this configuration with whatever your slope was from the previous calculation. Boom, it calculates the y-intercept. It's a prediction. This is your prediction model. It's not saying that these things actually are fact for every single terabyte versus price in the context of our example, but it's predicting what things would be. Your slope would be predicting, and again, whatever number we end up getting, and I'll show what that is in a moment. Your slope is predicting what the change would be in the price given a predetermined change in the terabytes. Your y-intercept is predicting what the cost would be if, I guess, the terabytes were 0, which doesn't really make much sense, but that's actually what the y-intercept is. It's 0, whatever that number is. It's kind of weird, I know, but Finally, let me just write down this statement, and then I'm going to jump back to my calculator for a moment. I mentioned the residuals. The residuals are calculated in the following way. Observed minus predicted. And I'm going to show you exactly what that means in a little bit. But it's your observed data point, meaning the actual data point on the scatter plot, figuring out the y value minus the y value of the prediction. The prediction is the line of best fit. That is the prediction model. I'm going to show you. It's going to be great. It's going to be wonderful. Okay. Let me jump somewhere real quick. I just want to make sure I got the right piece of information written down. Good, 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 and good. Okay. Let me jump over here. There we go. Focus the screen. There we go. Boom, boom. Now, first, let me write down something on the board in regards to this particular problem. Let me write down something on the board. I am going to write down the following. Now, again, I'm not putting this into my notes. I'm just kind of visually showing you what the heck's going on here. But the y hat in this case would be 142.18. I'm going to round that up to 1.8. X minus 296.31. So that would be my prediction model. And again, I used a y hat in this case. Now, if I went back to the actual problem in the textbook, you might see it written like the following. You might see it written as, well, my y variable is, of course, price, and the x variable is capacity. So you might see it written as this. I'll just abbreviate it to CAP. Again, that looks very strange. That looks very strange to see it written like that. But this is what they would end up doing. This is what they could, or you might end up seeing in regards to variables and things of that nature. Very strange. Very, 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 very strange. Now, let me go to my graph to kind of visibly show you something here. And I am going to go on my scatter plot up to this point right here. There we go. Now, again, I just want you to visibly see this, what's going on. You can see that blinking right there. Sorry, I was looking at the screen. But you can see it blinking right there. Now, that point that is blinking, the point that is blinking is the observed point. It is an observed point. It is the observed point 12, 1079.99. That's an observed point. What is the predicted point? The predicted point, let me move this paper underneath out of the way. Hold on. It's really bugging me. Aha, there we go. The predicted point is based on the equation that we got from the line of best fit. I'll move this there, move that there. There we go, much better, much better. Now, the line of best fit in this case, of course, using your A and your B there, I would type in 142.18 parentheses. I type in a 12 plus 1079.9, no, 1079.98. What am I talking about? Minus 296.31. There we go. Don't know where I was going with that for a second. I'm going to make a prediction based on the prediction model. And if I make that prediction based on the prediction model, chapow, it gets me 1409.85. So there's the observed. The prediction was 12, 1409.85. The residual again is observed minus predicted. Observed minus predicted. Did I write that down right? Oh, goodness gracious, I'm losing my mind. Yeah, I was just making sure of something. It's observed minus predicted. Now, yes, that'll get you a negative number. That'll get you a negative number, and that should make sense visibly with the graph, because that point ended up being under the prediction model. Under the prediction model. And one way that you could verbally explain this, yes, it gets a negative residual, but a negative residual in this case is that the prediction model, the line of best fit, overestimates the cost. Just to be very clear about that, it overestimates the cost. Now, I'm going to write something down in a moment in regards to this prediction model, in regards to any general prediction model. We can use this model to make a prediction of the cost based on the capacity in terabytes. Let me repeat that. We can make a prediction of the cost based on the capacity in terabytes. You cannot do it the other way around. You cannot predict the capacity based on cost. When you look at this model up here, this one at the top right here, you can plug in a variable or a number for the variable. You can plug in a number of terabytes, the capacity, and it would predict the cost. But you cannot do it the other way around. You are not allowed to. You cannot plug in a cost of like $50 and then figure out how many terabytes that is, because that prediction doesn't work the other way around. What you would have to do instead is you would have to rerun the linear model, the linear regression. You would have to rerun the linear regression, switching your L1 and your L2. You would have to do that. You would. Different slope, different y-intercept. Fun fact, you would actually have the same R value. You would have the same R value. But you would have a different slope and a different y-intercept, and you would have to find a different prediction model in order to do that. I'm going to write some of that stuff down in a little bit. We'll get there. It's going to be amazing. Now, I want to look at these residuals real quick, because I'm going to calculate that in a moment, but I also want to look at the residual of that graph. How does one look at the residuals? Well, check this out. This is going to be helpful. Incredibly helpful for all of you. If you go back to your lists and you go up to, let's say, like L3, for example. Well, you can do this in one of two ways, really, but this is probably the easiest. There is this function called INS, insert. And insert is written in yellow just above the delete key. You can see the delete key right here where I'm kind of pointing at the bottom. INS stands for insert. And if you go up to L3 and highlight it on L3 and you hit second delete, it actually spaces out the list so that you could put in a list of your own or any list that you want. And what's nice is, well, I have a residual list that I would like to look at. So if I wanted to insert the residual list, I would just have to hit second stat, which would take me to my list of lists, go down to resid, throw that thing in there, hit your enter, there's your residuals. There are your residuals. Again, your residuals are observed minus predicted. Positive residuals indicate that it is a point above the line of best fit. Negative residuals indicate a point that is below the line of best fit. And if I go down to, there it is, that one right there, for 12 terabytes, you can see the residual that was calculated, negative 329 and change. That is 1079.99 minus 1409.85. Again, these are going to be a bit more rounded. They're rounded because, well, I rounded my slope and y-intercept, and the calculator did not. But that's how these residuals look. Oh, it's so wonderful. It's so wonderful. These residuals are going to come in handy. Oh, you're going to see that. So let me go back to my notes. I'm going to write down some information. Let me see here real quick. Ba-boom, ba-boom, ba-boom. Cool. So now a couple of notes here that I'm going to make. Y hat equals b sub 1x plus b sub 0. You can predict y values from plugging in x values, not the other way around. Not the other way around. Let me erase that thing up there so you can see a little better. But not the other way around. Just to be very clear about that. Sometimes they're going to try and trip you up on stuff like that, being like, hey, why don't you do this? And you're like, oh, we weren't allowed to do that. Yeah, I know. Yeah. Now, in our example, we had a b sub 1 equal to 142.18. Now, what that actually meant in context, slope is a rate of y over x. I'll erase that other thing as well, because you can't really see it now either. Hold on. Now, it's a rate. Slope is a rate. It's a rate of y to x. Now, what this means in context is and I'll put it over 1. I'll put it over 1 right there. For every additional terabyte, I'm just abbreviating, of capacity, we predict a cost increase of 142.18 or 142.18 or $18. I can't even talk right now. $142.18. Nailed it. But it's a rate. And I want to be very clear with how I worded that. For every additional terabyte, which is the x variable on the bottom of that fraction, we predict, again, predict, not saying there will be, fluffy language, we predict a cost increase of $142.18. The other example that I can kind of point to is the y-intercept, which in this case was negative 296.31, negative 296.31. Now, the context of this may not make much sense, but again, it's a prediction. It's weird. In context, with a 0 terabyte capacity, we predict a cost of negative $296.31. Now, clearly, what? That doesn't make much sense, and it shouldn't. And that would be something that would be noted. If you had to state the y-intercept in the context of the problem, or if you were to interpret the y-intercept in the context of the problem, this is the statement that you would make, but then you would make an additional statement of, well, 0 terabytes is nothing. You're basically paying negative dollars for nothing, that doesn't make sense in the context of the problem. Although the slope does make a lot more sense. We're predicting a cost increase of $142.18 for every additional terabyte of capacity. Yeah, absolutely. That's exactly what we're predicting. Again, predicting. Okay. Let me see here. I have a couple minutes left. I'm going to save. Yeah, I'm going to save R squared. Yeah, I'm going to save R squared because R squared does deserve more. Well, I can't even think of the phrase I'm looking for. It does require, it does deserve more time, basically, so to speak. Before we leave, let me show you one last thing. Now, I'm going to show you, not actually write it down. Keep that in mind. I want to show you and not actually write it down. Now, we didn't run the linear regression without the supposed outlier, which obviously we should, but I'm not going to do that right now. Instead, I'm going to do this. Now, just watch. Second y equals, actually, you know what? I'm going to get rid of this line as well. There we go. I got rid of my y equals thing, but second y equals, go into that plot. I'm going to go down to L2. And I'm going to replace L2 with my residual list. Second stat, resid. What I am about to look at is the residual graph. Now, this residual graph is going to mean a lot in a moment. I'm going to zoom 9 it in order to resize the window, of course. But I need to see what this residual graph looks like. Zoom 9, boom. Now that is interesting. What's really interesting about these linear models is the fact that they're going to have you do all of that work, and then they're going to ask like that final question of like, oh, well, what did you notice from the residual graph? And from the residual graph, I don't know about that point. I mean, obviously, we're assuming that is an outlier, and we would have to run the linear model without that outlier, which perhaps we would get better results, which we'll see next time. But if you include that outlier, the residual graph has a pattern. If you include that outlier, and I don't know what will happen if we don't include the outlier. If we don't include the outlier, maybe we wouldn't see a pattern. I don't know. But there seems to be something like a pattern going on in the residual graph, which means, conclusively, with this model, a linear model is not appropriate. Sometimes that happens. It's really weird. We're going to jump into more of this next time, of course. Next time, I'm going to jump more into residual graphs, and I'm going to jump more into the R-squared definitions. I am going to assign you something out of the book, and this something out of the book will be based on stuff that we have done, so you will be able to handle it. Of course, it will be based on you doing things with your calculator, but we'll get there when we get there. Anyway, I'm going to sign off. Y'all have a fun day. Woo? I don't know. Cool. Good night.